Why do you think that, or people think, or just your reflections into fault-tolerant quantum computing? Is it needed for scalability, and why?
I believe this is like the most relevant things for like fault tolerance and then for the scalability. I think it's the purpose of like AI or machine learning models. In this era, we believe, and everyone, I think we agree, is like the AIs and machine learning is going very fast. So of course, we're in the field of quantum. We believe like we want to go as fast as the AI and the machine learning itself. So we as a quantum developers, the machine learning that accelerate in quantum, we believe like quantum would be the fast track that can accelerate on training so that the machine learning and AI can go more rapidly compared to the classical one. So I believe in terms of like currently, we are in a stage like we want to grow in a more scalable. So I believe in order to reach this direction, fault tolerance is the first thing that we should consider. Since like we are not really in a mature stage yet. Everyone is acknowledged that. So we're still researching on this phase. So in order to be quantums to be very scalable in the future, I believe each and every individual of us is working toward this fault tolerance, focusing on different areas, either error correction, either error mitigation, or either on quantum chips or any architectures wise that we want to accelerate toward this direction.
Fantastic. Thank you so much. Allow me to go to Dr. Suzanne. Dr. Suzanne, as you know, the theory for quantum physics was developed, and indeed in the Middle East we did not have enough fortune to have a strong contribution. Contribution was there, but it is indeed to a limited term. So what do you think about, as we are witnessing a revolution nowadays, it's moving from the theory into the application, and the Middle East with the young population, educated people, and we are feeling that we have the opportunity now to contribute to the quantum industry. What is your reflections, and what do you think would be the most important things?
Okay, thank you, Professor, for this question. In my point of view, I can see that Middle East can contribute to the development of general-purpose quantum computers in this field in several ways. First, in the way of the research and academia field, because now many universities and research institutions in Middle East are developing programs in quantum computing and related fields. So the collaboration is very important with global institutions. This can enhance research outputs. This is the first point about the research and academia. Also, the investment in technology. Many countries like the United Arab Emirates now, they have significant investment in technological innovation, which include funding for quantum research and startup. Also, we have inventors in Middle East who innovated the most cutting-edge main memory for quantum computers called Q1 RAM. So all these efforts are working together beside the government support. We need the government support because it's significant in promoting this effort to have a real contribution to this field as a Middle East. That's my point of view.
Fantastic. This is an optimistic message, and I think we should believe in it. And I think
yes.
Also, we are not seeing ourselves as an isolated part of the world. We are an integrated part of the world, but we should play our role as a key player, I hope.
Yes.
Now, our expert, our engineer Ahmed, you are our expert, and we wish to hear from you reflections into IBM's move to multi-chip quantum systems, like the Quantum System 2. What is your insights about it?
Yeah, actually, the main reason behind shifting to multi-chip quantum systems is driven by the scalability limits of the monolithic processors, right? Because other than that, the same will be under Moore's law, right? We have a single chip. We need to infuse a lot of qubits on the same space, which is impossible. Definitely, if you look into the architecture of the quantum system, we have many challenges, like the fabrication itself of the qubits. Any one defect can ruin the entire system. And even the wiring bottleneck, as you can see in the background, I put it on purpose just to imagine how many connections and coaxials that we have inside one single quantum system. which is definitely with the increase the number of qubits, it will be very challenging to have all these connectivities and to maintain a lot of qubits at the same space. And that's why IBM started to get a new chip, which is Heron. This is one of the best chips that we have currently. It has 56 qubit. We have 3 versions, and this is the latest version, R3. So this is manufactured to be able modular, where we can have it like that image to my right. Okay, so we have multiple systems working together as one system. So the quantum system, this is what we call it, the quantum system 2. Okay, so the quantum system 2, it's like a scalable quantum of data centers. It's integrate multiple quantum processing units and the classical controls as well, and the middleware where you can exchange the information. So the modularity will allow us to increase increase our throughput, the processing power, incremental upgrades. It will be easy, even the maintenance as well. And this will pave the way to the utility scale and eventually the full tolerant quantum computing. But yeah, how IBM can do that? The tunnel coupler, this is the new technology that connects all these chips together. We have many different types. I will not take much time on it, but I'm just telling you that it's a very emerging technology that IBM has to support the multi-chip architecture.
Fantastic. Indeed, last time I met Petra, she's, I think, the European Middle East representative for IBM. She said that this is gigantic refrigerator, has 3 systems now in it. And that was a couple of years ago. I don't know if it was, the capacity increased or something.
It is, because now we have like 3 in system 2, quantum system 2. We have 3 modular Heron qubit processors that working simultaneously together, which is increased debut.
Fantastic. That's a very indeed insightful update. Now, Dr. Muhammad, we need you please to tell us more about the all-purpose quantum computer. Tell us about hardware and software bottlenecks. What would make it a game changer? And what do you personally think about it?
Okay, well, a general purpose quantum computer as the ultimate goal of quantum computer like IBM, Google, and many firms around the globe. So to achieve general purpose quantum computers, we have to build quantum computers in 2 perspectives, from hardware perspective and software perspective. From hardware perspective, there are many fault-tolerant quantum computer systems should be built. First of it, we have to build a universal quantum processing unit. We have to build fault-tolerant classical quantum gateway, and we have to build an efficient main memory for quantum computers and other controlling systems that connect both classical systems with these quantum component systems. For software, we have to build 2 main items. First of it is quantum compilers. Quantum compilers should take the code that should be coded and should be written by quantum computer programmers and convert it autonomously and automatically without any concern from the coder, from the programmer into the underground hardware, into the infrastructure hardware, which contain quantum gateway, fault-tolerant quantum processing, and fault-tolerant quantum main memory. The second item from software, we have to think to build what's called quantum operating system. So the main objective from quantum operating system is to take the code written by the programmer and handle the quantum resources in real time to achieve multi-user quantum computers and multi-applications quantum computers. This is the ultimate goal of general purpose quantum computers, to implement all applications, quantum artificial intelligence applications, quantum optimizations, quantum sensing, quantum image processing, quantum security system through general purpose quantum computer. What we do now, we do know what is called a special purpose quantum computer. In a special purpose quantum computer, the researcher, the developer, the user should be expert in quantum computing to build his circuit by its own and try to implement this circuit. So this is why we call it special purpose quantum computer.
I totally agree. Scalability, the way we talk about it now, it is about the capacity, but I think scalability is more than that. It's about how it can be scalable from business case, how it can be from application-wise. And of course, we need an all-purpose quantum computer to be scalable at the application, at the daily life applications, as a matter of fact. 100% agree.
What is the issue now? That both researchers, firms, young developers, they are in a rush to make showcases. They don't focus to build and solve the problems of the infrastructure and build based on. They are in a rush to achieve high application, quantum optimization, quantum machine learning, and we have major problems and major challenges in the infrastructure of general purpose quantum computers. This is why will make the progress towards general purpose quantum computer will be very slowly.
I totally agree. We're still at the early stage, even at the public level. Still, people doubt, and some of them call it a hype. So we're still at the early stages. But as quantum is very much accelerating, I hope that we can accelerate very fast in this direction. So allow me to go to Dr. Heng. Dr. Heng, artificial intelligence is taking a huge, attention from the industry, from the developers, from governments, from investors. And again, quantum is emerging as well, and they will indeed meet at some point. Who do you think should lead who? Do you think AI should lead the way that quantum is being developed, or the other way around? Do you think a quantum capacity can serve AI, or AI can serve as well developing the quantum computers? What's your reflections on that?
Thank you so much for your question. I think it's like a big question, and then it's like everyone, even we are in this field, we still cannot figure out which one should go first and which one should be the accelerating in this way. So to me, personally, I believe they should be go in the same directions. We cannot deny the fact of AI and machine learning, their own workload and scalability. But at the same time, we can see like there will be the bottlenecks for the AI and machine learning models and the workload itself, which is still the bottleneck as now. It's too big. It's too large to train on the classical machines. So I believe in these bottleneck, where's the quantum come in? So I believe quantum chips, quantum machine, the QRAM and everything will be accelerated in the machine learning or AI in this way. So that is why I think the AI and the quantum should be coexist together in these research and in the future as well, since this one is not just a physical level. Professor Dr. Muhammad is also mentioned about this one. We not just focus on physical level for quantum. I believe quantum in the future is about general purpose quantum computer, which we can solve everything, all the problems that we exist. We're trying to this way, but eventually probably there's a few problems that is too small that we don't need any quantum to solve these. But we believe with the very large and scalable workload of the classical machine learning, the data that needs to be trained, I believe in this direction, maybe quantum can be accelerated in the coexisting of the architectures and also the application wise. So that's why in this bottleneck, I believe quantum has a bottleneck, whereas it's not open for a higher application level. So where this quantum has to be mismatched to the real world application, where I specifically for the AI and machine learning. So I believe in the quantum that we should switch into the perspective of what if we want to accelerate in the machine learning? What about the optimization? Maybe quantum can have a very friendly ecosystem where the application level can really apply the quantum more easily, since the infrastructure now is not really friendly yet. Even we have a queue control, penny length, and many higher application level, but I believe we should accelerate more in this way. So I believe in this way, maybe machine learning and quantum can go in the same direction to accelerate each other's. Yep.
Thank you so much. I appreciate it. Yeah, it's very insightful, and I agree with you. It's a thing to be figured out, because it might be 2 or 3 things together. It's not necessarily to be in a certain frame that we are envisioning. Dr. Suzanne, reality check, because when we are talking nowadays about the quantum industry, it's in innovation as well. It's not only research, it's not only scientific discovery. It's about developing the workforce. It's about developing their capacity. So what do you think would we as a strategist, what should we do to develop the right workforce in Egypt, for example, as a case, towards being true contributors, to build the capacity for example, developing the all-purpose quantum computer?
Okay, thank you, Professor, for this question. Preparing a workforce in Egypt, we need to develop general purpose quantum computers. This may involve several strategies we need to work on. First, we need sophisticated and well-established educational programs related to the quantum computing and all other fields to have a strong foundation for this field, and also to have more experts in this field. We also can create internship programs in research institutions and tech companies that focus on the quantum technologies. We also should encourage students to participate in the collaborative research projects that involve real-world quantum computing challenges. Furthermore, we also need to establish strong mentorship programs and opportunities for youth and newcomers and researchers, where experts and professionals can guide this process and these programs to have good foundation in this technology. So I think we need collaboration more with all these ways to have and to build or prepare a workforce in Egypt.
I think the wealth, the upcoming wealth, besides the knowledge wealth, it's a workforce. It's a capacity wealth. You know, economic of countries, economies will depend on the workforce of these countries, rather than kind of natural resources and whatever. So I totally agree, and this comes at the top priority for nations, and that's why this kind of gathering is really very much important.
Yeah. Now, so the global collaboration.
Absolutely. Please go ahead if you wish to. Yeah.
Yeah, the global collaboration between all institutions and companies, firms, this will all make it easy for us to have our workforce in Egypt.
Thank you so much. Dr. Ahmed, indeed, you provoked us with the background that you have. So we know in your left is the system 2 that has these 3 modular quantum computers. What is in your right? What is that?
Okay, this is the Osprey. It's one of the IBM quantum processor. I just put it to show you the layers that we fabricated inside a single processor. You have the readout layer, you have the qubit layer, and you have the read layer. So this is just to illustrate what is what we have at the end of each quantum system.
Beautiful. Yeah. So that leads us to L-couplers. What you can tell us about L-couplers? How, more specifications, and how do you envision that L-couplers really will lead into a further step?
Okay, this is really a very good question, because this will pave the way to achieve the quantum advantage. But let's define what are the tunable couplers that IBM came with. We have different types of couplers. Okay, so the first type is the C couplers, and the C couplers, IBM created this to control the interaction between non-local qubits on the same chip. And the couplers, the tunable couplers itself, it's a like electronic circuit, where, as we know, the noise comes from the crosstalk between 2 qubits. So this is one of the challenges that we are facing. So what IBM think about, we can put an electric circuit between these 2 qubits, where we can control the frequency. And when that the coupler is off, so we are making a destructive microwave signal. So it will cancel the interaction between these 2 neighbor qubits. So there is no interaction between both. But if we want to have like an operation or something, we turn it on and amplify the microwave frequency. So this is the whole idea behind the tunable coupler. So the C couplers, it work on the same chip, with non-neighbor qubits. And the M couplers, which is the other type of couplers, it works between two different processors at the same chip, like what we have in Crossbell. It has been announced last year. And the L coupler, this is the game changer, where it will connect two different processors at distance. It's not resides on the same quantum system. And the first demonstration of the L coupler, it was in Flamingo. This is two chips of Heron. So it's one processor, consists of two Heron processors, 156 qubit. And we are, IBM by this year creates more than 1,000 physical qubit system. And in this case, we are aiming to have or achieve the fault tolerance where we have clusters of quantum computers in this way, so we can expand the number of physical qubit and now cluster it and represent it as a logical qubit later on, which is one of the requirements to have a fault tolerance or achieve the quantum advantage.
Perfect. Thank you so much. Indeed, I think we are coming close to the last round. And maybe, Dr. Muhammad, you tell us from someone who really was trained as a mathematician, moved into a data science, and ended up to an expert in quantum technologies. What is your, let's call it take-home message? What was your point that you wanted to highlight to young researchers?
For young researchers, I advise them, don't rush in application. Don't be rushed in to apply quantum machine learning in weather prediction in high application. We are so far from achieving some advantage right now using quantum computing. We have to develop quantum computing systems, whether maybe end-to-end quantum computing system or hybrid classical quantum computing system, such that the computation on this system should achieve advantage. But if we go to massive applications such as prediction whether using quantum machine learning, using our results today, we will not make any advantage. We will not make any sense. Always large language models is the best. Always classical machine learning is the best. But we have to work slowly, try to solve the problems from its background, solve the problem challenge by challenge, then connect them, because quantum entanglement is very critical phenomena. Because developing classical systems is totally different than developing systems using quantum computing. In quantum entanglement, we must develop the entire system. Because of entanglement, we have to develop our algorithm using all the entire system. We cannot ignore part like classical, but we have to integrate the whole system. So we have to work slowly and solve the problems from its background to build and go towards general purpose quantum computers. This is my key message.
Thank you. Thank you so much. I think everyone here agrees. Yeah, absolutely. This is it's more than just a simple problem that you need to handle. This is a new era of addressing knowledge and addressing nature, as a matter of fact. Now, Dr. Heng, it's a tricky question again. Now, we are having a classical system, and this kind of classical computing with its own heritage, it's been very successful in many problems, and it's been successful even for AI. And we are having the quantum computing, which is promising even further going beyond. So how do you think is the architecture should be of having a hybrid quantum classical AI motivated application or AI motivated structure for the quantum computers?
Thank you so much for your question. So I believe this would be when we think about the quantum machine learning where we belong. So I believe I'm categorize myself in the hybrid quantum machine learning or hybrid classical machine learning where we apply the quantum into this one. So I think there will be 4 aspects that we can accelerate on this one. First thing first, I believe on the architecture wise, where we have to have a very tolerant architectures. Also, we focus on the application aware coupling, where your previous question is about. I believe in order to accelerate the AI workload more effectively, the coupling, the interconnection on the qubits, on the connectivity on the chip itself is very crucial. Otherwise, everything is nothing. It's all about errors. So I believe in terms of like a very large scale of AI workload, connectivity, compilation, translation on the chips and on the logical level should be considered very wisely. And the third one, I believe on like the high yields on the chips itself. So I believe in terms of like the resource efficient quantum memories, where we can load, where we can offer, store, and everything should be reconsider wisely. And also last but not least, I think it's about the instruction itself. Since currently the instruction is still very low levels, unless you are in the fields, we can use it very easily. But if you are from the AI background, the machine learning background, you have to switch yourself into like how you can use it. It's more elaboratively. So I believe in terms of like, maybe we can introduce like ISA instruction so that we can use the memory, the RAM more efficiently and more scalable in order to reach into like the scalability and fault tolerance in the near futures.
Thank you. Thank you. Beautiful. Indeed, Dr. Susan, I think you have a nice story to tell us about Q1 RAM. What is Q1 RAM, and what do you think it's going to be in the next couple of years?
Okay, thank you so much. Q1 RAM is innovated to be the fastest ever quantum main memory tailored for scalable quantum computers. It's an essential component not only for developing general-purpose quantum computers, but also for developing scalable quantum computing products. Any products that can handle with large data sets, applications, and also massive number of users. QRAM or Q1 RAM is the missing piece that allow quantum computers to interact with large classical data ecosystems that dominate our modern world today. It makes the transition for the quantum computers from laboratory instruments to products that can be integrated in the enterprise IT infrastructures, whatever the technologies they use, and to be able to develop scalable quantum computers, we need this missing piece, and to generate and also start to create general purpose quantum computers. So it's very essential to focus on this invention and to try to deliver it to the enterprises and firms that may use it in the future to have in every home a quantum computer using our QRAM or Q1 RAM.
Thank you. Thank you so much. Hopefully we'll hear more news in relation to that. Thank you so much. Dr. Ahmed, you know, IBM always is putting roadmaps, and it's indeed the roadmaps that they do is not just what they do. It reflects into globally how other ecosystems is responding to that. So what do you think is the current strategy or the next strategy will be to scale?
Okay, scalability, it's this is the ultimate goal for any quantum vendor and the market, regardless of the architecture of the quantum machine, whether it's a superconducting like IBM, Eintrab, Photon, whatever the architecture is. But still, the way that we are trying to achieve the practical quantum advantage is about scaling what we have in place, like the multi-chips. However, I wanted to emphasize on Dr. Susan about the quantum RAM, which is one of the main components that we need. Actually, all the big vendors of quantum computing, they never think about it, or maybe they put it on a later stage while they are trying to overcome the current challenges that we have in the current quantum computers. However, if you think about all the use cases that we have in the market, still we are working with the classical, quantum, classical. So this is the main order. Okay. So can we have a way that we offload some classical workload to a quantum? Because at the end, all the data that you need to transmit, any use case, quantum security, quantum sensing, networking, whatever, we need a memory, which is definitely an essential component in the building the quantum ecosystem. And this is one of the milestones that IBM started working on it this year. However, the QRAM, I think Dr. Muhammad Yani had this famous patent, many patents around the QRAM, which is very, very, very advanced. I saw some statistics about the performance comparing the existing ones. Really, this is a promising. However, if we can summarize this, IBM mentioned that we will not achieve the quantum advantage or the quantum supremacy and overnight. IBM was HSBC Bank this year. They announced a successful implementation based on Heron processor to improve the bond trade prediction accuracy by 34% on a real market data, which is a huge achievement where we can say, okay, we are on the right track. Definitely with the ecosystem, with the innovators that we have, definitely in Arab countries or even the partners of IBM, they are building a lot of algorithms. For example, we have the marketplace. Dr. Muhammad mentioned about the compiler. IBM is trying to enrich the platform with what we call it the Casket add-ons, where we are having a marketplace that the partner can sell or commercialize their work, their research. And this is the benefits for the business partner, for IBM, and definitely for all the world trying to solve problems using quantum computers.
Thank you. Fantastic. This is very much comprehensive indeed, and it implies a lot of details, a lot of ecosystem involved into it. Dr. Muhammad, do you would like to tell us last take-home message? Do you like to tell us about your patents? Do you like to tell us what you wish to achieve the next 1 year? It's up to you.
Okay, for our patents, it's my pleasure that this patents is accomplished because the effort that introduced by Professor Muntasir, by Professor Hisham Naish, by Professor Mahmoud Aati, they make these patents in real patents, and they make them the major efforts in these patents. So thank you for you, Professor Muntasir. Thank you for Professor Hisham and Professor Mahmoud Aati. For patents, this is always new technologies have opportunities. If we look through history, always opportunities appears in new technologies. And we in the Middle East lost the first revolution, first industrial revolution, lost the second industrial revolution, lost the third industrial revolution, but now we are in fourth industrial revolution. We have both classical artificial intelligence and quantum computing. Quantum computing is a new theory for computation. We try to make the computation for all applications and all fields from scratch. So there are many challenges, and when we solve some of these challenges, we can make progress. We will be key pillars and key players in this technology. So we have to focus to solve the challenge. We have to focus to fill gaps in this technology. Then we can make important innovations, and we will be key players in this technology. This is my final message.
Thank you. Yeah, it's a blue ocean. They call it a blue ocean, where you can create the market and you can dominate the market. Let's hope so. Dr. Heng, again, forgive me. I'm always having tricky questions for you. So tell us something that you think we don't know. Tell us something that you think it matters for quantum and AI. I do know you don't know what we know, but tell us something that you think that you wish to tell us about for the quantum and AI and the developments that's currently happening. Anything you wish.
I think that's very tricky since everyone is very expert in your domain knowledge already. So I believe one of the main things that I'm trying to do this day with the quantum and the machine learning and AI field, which is I'm personally trying to focusing on the compilation and transpilation, where I trying to do the qubit reset. So since the number of qubits is still limited this day, even the IBM roadmap is going very fast, but in the experimentation wise, we still limited in terms of the number of qubits to execute the scalable AI that they have it. So I believe in what I'm doing this day, which is like we're working on the reset qubits, where we want to reset the measurement as many times as possible, so that this is where we optimize our execution or experimentation for a better scalability in terms of like reaching the number of qubits that we want to execute this day. Yep.
Fantastic. I totally agree. It could not necessarily be too many qubits. It could be a high quality applicable system that can does not necessarily only computation. It could be characterization, it could be testing, it could be security wise, whatever. So this is fantastic. This is lovely. Thank you so much. Dr. Suzanne? I think, yeah, because, yeah, exactly. I think she has a connection problem. So then to our good friend, Engineer Ahmed. Engineer Ahmed, what do you think would be the most, and forgive my question if it's not really addressing a correct problem, but what do you think will be the low-hanging fruit upcoming that will make a game change in the industry landscape?
Okay, it's a really insightful question, because the low-hanging fruit, we can think about it and the problems that it has industry interest, and we can prove with the current technology, even using these noisy systems that we have, we can have a progress. It's not, as I mentioned, it's an overnight realization of quantum advantage. Still, it will be based on industry and the use cases. It's not one size fits all. We are trying to build a quantum USFIL, as I mentioned. This is one of the two missions of IBM, to bring a secure, definitely quantum to the world, and bring the useful quantum to the world as well. The innovations that we can have in the industry, in the quantum industry, with the ecosystem, with the communities, like what we are doing now, definitely at the end will make the progress of the quantum computing in a different way, more than the classical. If we look into IBM roadmap, it's very promising. Maybe we don't know what we will do after 2-3 years, but we are always raising the bar, not only with us, but if you read about IBM paper, all the achievements, it's either IBM plus a business partner, or a university and academia. So this is what I can say from the low-hanging fruits that we have. We are changing all the research that we have into running applications that open to be used by the community. One use case, IBM partner with RACN for more than 1 year to develop a quantum algorithm, where Cleveland Clinic in US, they took the same algorithm 2.5 months. You got the benefits, 1 year of research. Now 2.5 months, they were able to adapt it in the drug and doing chemistry calculations. And as well, Lockheed Martin, the same, they're working on the same algorithm. So at the end, the collaboration of the ecosystem is I think this is the winning force in the quantum ecosystem. Yeah.
Thank you so much. It was a great pleasure having you all here. If you allow me, I think what we know of what we don't know is something, but what we don't know that we don't know is huge. We know that we don't know a lot of things, but even there is a hidden one that we even don't know that we don't know. And that is a great message for all scientists, that will indeed highlight the opportunity. The opportunity is always huge. So, and I hope second message is that I hope that our relations will not end up here. Again, thank you so much, Professor Mahmoud. Your efforts is unbelievable, and reaching out despite that you are well achieved. You are a high achiever. You have achieved everything that you wanted, but you're still acting like a dynamo. And this is a venture that we can even develop. So I hope that we stay connected with our colleagues across the world, and the opportunity is really huge. Thank you so much.